15. It's chapter 15 when we did solubility. Nope. We already finished 16. Yes, we did. 16? No, 15 was really short. 16 wasn't necessarily so short. 17. But we're gonna work through some problems over 15 and 16 and make sure we understand it. Okay. Before we move on to 17.
17 is the last chapter?
Depends. If we can get into some nuclear chemistry, then I would like to, but it's fun stuff, guys. Okay. Well, we have a whole week. I mean.
I know a whole week to study for.
Okay, so let's look at this. Calculate the concentration of ions in the following saturated solutions. Okay, so if it's a saturated solution, that means it's at equilibrium, right? So the KSP is equal to the concentration of the silver and the iodine. Okay, so AgI dissociates in equilibrium into Ag plus and I minus. Okay. So when we get our KSP equals products over reactants. This is solid, so we don't include it. All we do is include the products. KSP equals the concentration of Ag plus times the concentration of A minus. It should be a minus. Okay? All right, so this is what we end up with. So calculate the concentration of ions in the following saturated solutions. The Ag plus ion is 9.1 times 10 to the negative 9. So what does that mean about the I minus? It's the same, right? Because they have to be at the same concentrations, essentially, for these two. If this is 9.1 times 10 negative 9, then that's 9.1. Because KSP equals S squared. So whatever one is, the other one is also. Okay? All right. So let's see then. Let's see for B here. So B is a little different, right? What's different about B?
There's 3 OHs.
That's right. There's 3 hydroxides. Okay? So you're going to have to relate that to the Al3+. Okay, what is the KSP equal to here for B? KSP equals what? Concentration of Al3+ times the concentration of OH minus
Is that to the third?
cubed.
Is it? So it's not, it doesn't go by the coefficient, it goes by how many?
It does go by the coefficient because let's rewrite it this way. We never wrote the reaction, right?
In a balance.
AlOH3 in equilibrium with Al3+ plus 3 OH minuses. Okay? So my KSP equals the concentration of Al3+ times the concentration of OH minus 3. Okay? All right. guess we'd want our KSP here. KSP equals 8 times 10 to the negative 30. So for B, the KSP is equal to 1.38 times 10 to the negative 33. So we would look that up on a chart, but since you guys don't have those in front of you. Nope. Oh, yes, you do. I'm sorry. Okay, so what are you guys getting for that?
So he took the cube root and cubed it, and neither of them work out right, so I have no idea.
Okay, so the KSP here is equal to this times that, right? So if I divide OH minus cubed by KSP, that should be my answer. KSP is 1.8 times 10 negative 33 divided by 2.9 times 10 negative 9 cubed. Is that what you guys are doing? Okay, what are you getting? Okay, 7 point what? 7.4, 7.38, okay. Times 10 to the negative 8? The actual answer is 7.38. 7.38 times 10 to the negative 8. You're going to take this KSP and you're going to divide it by this cubed. Divided by 2.9 times 10 negative 9 cubed. That's it. That's a good way to do it. Make one up. Okay, so that's pretty. Those are pretty basic. You can look up the KSPs from the chart. You can find the concentration and everything. We could have done that here as well. So if we would have looked up the KSP for the first one, we could have divided it by 9.1 times 10 negative 9, and we should get 9.1 times 10 negative 9. The KSP of the top one is KSP equals. Okay, So it would have worked out either way, but we didn't need to do that because we knew that the concentration of these have to be the same. Right? So whatever the concentration of that is the concentration of the other thing. But that would just verify it for us, I suppose.
So the only time they wouldn't be equal to each other is in the case where there's like some type of coefficient or subscript thing.
That yes, if it dissociates to have a coefficient, then it will not be the same concentration. But if it dissociates into 1-to-1 ratios, then it's the same. There, everything there would be the same. Yes.
And the concentrations would be given to us, right?
Yeah. Well, this question they are. So, in other questions, I mean, you'll have other types of questions, but this question, if you have a question like this, then the concentration of one thing is given to you. You can find the concentration of the other thing by knowing the KSP, and the KSPs would be given to you, so you could do that. Okay. No, we'll start easy. That's kind of the. Okay, from the solubility data given, calculate the solubility constant for the following compounds. So if S equals 7.3 times 10 to the negative 2 grams per liter, then what is the KSP of A?
That's the easy way to just figure out how many ions there's going to be and do that for the third.
Okay, so let's do this. So SR F2 dissociates into SR2 plus 2F minuses, right? Okay. So the KSP here is equal to the concentration of SR2 plus times the concentration of F minus squared, right? Okay. So what is if we simplify that, KSP equals what?
7.8 times 10 to the negative second cubed.
Okay, so we could do it this way, but we could simplify this whole thing, okay? We could just put S in for SR2 plus, I'm sorry, I forgot a 2 here. This could be S, and this could be 2S squared, right? Does everybody know why I forgot that 2 or what that 2 is? No? Okay, let's redo this. Let's start over. Okay, so this is going to be plus S plus 2S. Okay? And at equilibrium, we'll have S and 2S, right? So KSP equals the concentration of SR2 plus, which is S, times the concentration of 2S squared, because the coefficient is 2. Okay? So my KSP, if I simplify this down, is equal to 4S cubed. Okay? So square that 2, it gives me 4S squared times another S, 4S cubed. Now I simply have to do what? To solve for my KSP. Well, they gave me S, right? Except, what do I notice about that S? Is it in molar solubilities, that S? Is molar solubilities grams per liter?
No, it's moles.
No.
No, molar solubilities are moles per liter. Molarity is molar solubility. So this is in grams per liter. This is not molar solubility, so what do I do to it?
Find the molar mass.
That's right. Find the molar mass of SRF2 and convert that from grams to moles. And then it will be in moles per liter, which you want. You want it to be in moles per liter. to be able to use it here, because concentration here means what? Big M molarity, right? Means molarity. So we have to have it in molarity, which is easy to do by just simply converting that from grams to moles.
So on the bottom on the KSP where it says S, concentration of S multiplied by 2S squared, that 2S is coming from the F. And then, so you're going to put the coefficient out in front, like that, and then also square it.
You do both.
So let's say, like, hypothetically, if it was 3F, then it would be a 3S out in front, and then you would cube it as well?
Yes.
Okay.
Did you guys get something? Get an answer? What are you guys finding?
Oh, I see.
7.8 times 10 to the negative 10. Right?
You don't sound too confident about that. That's what it is. Yes. 7.8 times 10 to the negative 10. That's what you should be getting for your KSP in this case.
KSP is always in mole.
Because KSP.
Molarity.
What's that called?
Well, the KSP doesn't have units.
Yeah. Well, it's just two.
What's that?
Together.
It's negative 10. Excuse me.
So the KSP
Negative 10.
equals
It's just in
concentration.
molar solubility.
The S is in molarity.
2.
S is always in molarity, molar solubility. Okay? And you were given that in grams per liter, the solubility by mass.
Like 2S, you see down at the bottom it says 2S squared. Take the subscript of that. And the 2, and then you move it up front. Square. And then. Or what is it? Oh, because. Yeah, yeah.
Okay, let's look at B. So try B now. Set up the rice table if you need to so you can see how everything works out. Okay. I'm sorry? Fine. Calculate the solubility constant for the following compounds. So calculate KSP for this, just like we did for this one. Are you guys getting here? KSP equals 3s cubed times s? Yeah? Okay. So KSP equals 9s. I didn't do that right.
No.
Sorry. 27, right?
Yeah.
Is that what you guys were getting?
Can you show me how you broke that AG3PO4 and made it balanced?
Sure. Okay. So we have Ag3PO4, and this is your solid, and it's going to dissociate into Ag plus, but I have 3 of them to balance it, right? Plus PO4, 3 minus. I just need one of those. So this is plus 3s plus s. So at equilibrium, I have 3s and s.
Why is it 3s and s?
Because if I have one s here, I must get 3 s's here for every one of these. Okay? Okay, did you guys find a KSP? What'd you find?
5.44 doesn't tell you -8? Maybe?
Nope.
Screw that.
Okay, so yeah, that's more of what it should be.
Because remember, it's 3 data, and you're going to 3 on the front, and you're also going to use it power.
That's what I'm thinking. Did it the first time, and then
Okay, good point. Make sure you're converting that from grams to moles. The molar solubility, S is molar solubility. Yes, -18. Okay, So the pH of a saturated solution of a metal hydroxide, MOH, is 9.68. Calculate the KSP for the compound. Think about how you're going to go about doing that. Not the negative log.
I mean,
Anti-log. There you
I said wrong, but I put it
go. Okay, good.
Why did you put it in there?
It should be just kind of like those first ones we did.
After you put
The trickiest thing here is understanding why did they give me a pH? Because from the pH I can do what? You can find the POH. No, you don't need the. Yes. So you're going to want to find from the pH you can find your POH, and from the POH you can find what? OH minus ion concentration. That's exactly right. And once you know the OH minus, you know M. Okay, what are you guys getting for the KSP here? 3 point what?
2.29.
I mean, 2 point what?
29 times 10 to the negative 9.
Okay, that's more of what the answer is. So something just a little off. You're close though. I'm sorry? Sure. So here we have the metal hydroxide is going to dissociate into this metal and the hydroxide, okay, at equilibrium, because it's a saturated solution of it. So the molar solubilities here are S plus and S plus, okay? So the KSP is going to be S squared, okay with that? So here we take 9.68, which is our pH, and we take 14.00 minus that, and we get what? What's the POH? 4.32, okay? That's my POH. POH equals this. And then I take 10 to the negative 4.32, and I get what?
4.8 to the times 10 to the negative 5.
4.8 times 10 negative 5, which is my OH minus ion concentration. And so once I know that, I know what the other S is, or I can just simply say S squared. So 4.8 times 10 negative 5 squared. Okay. That would throw it off just a hair, right? Okay, so we're gonna move on to chapter 16 now. Chapter 16 over thermodynamics. So that's just kind of the solubility that'll get you started. There's a few homework questions about that, so make sure you do those. Okay.
There's one homework that doesn't have to be there.
I will be setting those due dates. Thank you for reminding me, because apparently you guys work by due dates only. So I have to set a due date in order for you actually to even look at the homework and work on it. So I will be setting that soon. Okay. Hopefully you guys have started them, because you don't want to get caught behind. Okay. Okay, let's calculate delta G naught at 25 degrees Celsius for this reaction, N2 gas plus O2 gas produces 2NO gas.
Is this chapter 16 or are we still doing?
We're on chapter 16 now. So that was chapter 15 that we were doing earlier. Now we're on chapter 16, thermodynamics. Okay, well, I haven't finished.
Okay.
Okay, so the delta G, not a formation of NO, equals 90.4.
I'm sorry, is the product gas or solid?
It's a gas. Okay, so let me just remind you. If I want to find the delta G naught from the delta G of formations, it's products minus reactants. Okay, just like it was with delta H's. Delta H, products minus reactants, just like it is for delta S. Delta S is products minus reactants. The delta G of the reaction here is equal to the delta G of formations, products minus reactants. Okay? This should be a pretty easy one. Products minus reactants. Let me ask you this. What is the delta G of formation for those reactants?
No idea.
0.
Zero.
Why?
Because they are
And the L?
That's right. They're in their elemental state. So that's 0. Okay? So whenever they're in their elemental state, it's 0. The delta G of NO is 90.4. Products minus reactants. But how many NOs do I have? 2. So what does that mean I do to this?
Square.
No.
Times it by 2.
Multiply it by 2. Okay? Don't square it. Multiply it by 2. Okay? And then it's products. It's not products over reactants, not equilibrium. It's products minus reactants. Okay? Products minus reactants.
Plus RT, natural log of Q. What's all that crap?
What? We'll be using that.
So this is just.
We haven't got there yet.
What was delta G again? Exactly.
I'm sorry, say it.
What was delta G again?
It's the Gibbs free energy, determined by the energy of the heat energy and the entropy. Well, hopefully this will help as we go through these problems. This is simply finding the delta G of a reaction from the delta G of formations, which is table data. Okay? This number came from a table. I didn't make you go to the table. I just wrote it down for you. But this is the type of information you would find in the back of your book, okay, from the appendix. In fact, let me just pull that up. So maybe we can just see here. Okay, so Appendix G in your book. Okay, so NO. Let's see if theirs is the same that I gave you. Okay, NO. The delta G right here for NO, 90.25. Let me make sure that's... Oh, that's the delta H. I'm sorry. I gave you the wrong one. Delta G for NO is 87.6. I'm sorry. Fix it, because I made a mistake. 80. Was it 87.6? 87.6 kilojoules per mole. Okay. Is the delta G of formation for NO. Okay, so is anybody finding a delta G not of reaction here? So simply you took 87.6 times 2. That's what it is. 87.6 times 2 minus 0 will give you 175.2. Okay? Products minus the reactants. This is the product, and it's multiplied by 2. Okay? Minus the reactants, which are both at 0. So I end up with 175.2 kilojoules per mole. Okay, let's try another one. C2H2. Okay, so what is the delta H of our delta G of formation for O2? 0. Okay, so we already know that one. We just need it for C2H2, carbon dioxide, and water. Okay. So let's find a few of these. Let's start.
Do we exclude the
C2H2. I'm sorry.
Do we exclude water, or is it left in this one? Like if it's a
You
liquid?
no, you don't exclude anything. This isn't equilibrium anymore.
So we don't.
This is thermodynamics. We're gonna move away from all of that equilibrium stuff.
Okay.
Thermodynamics, we're going to use the delta H of formation for anything that is not in its elemental state. And we're going to find it here. So C2H2 right here, 209.2. Okay? 209.2. 209.2. Okay? Is the delta G of formation for C2H2 kilojoules per mole. Okay? Now we got to find it for carbon dioxide. Carbon dioxide's right up here. Okay? Negative 394.36. Negative 394.36 kilojoules per mole. And for water, let's see if we can find water is. Okay, H2O, let's find the state. What was the state of this? Liquid. Okay, these others are gases. Gas at 25 degrees Celsius. Okay, so liquid water, negative 237.1. Negative 237.1 kilojoules per mole. Okay. And I purposely didn't tell you one step. Is that equation balanced? No. Do you need a balanced chemical equation? Yep. So long ago, huh? Chem 1 was so long ago. Haven't balanced them since Chem 1. Okay, let me give you a hint about these. Balancing these. These are easy to balance because O2 is all by itself, right? So I put a 2 here in front of carbon, okay? And that gives me 2 carbons. Hydrogens are balanced. And now I just have to ask myself, how many oxygens do I have? I have 4 here, right? And I have 1 right there. So that's 5. Okay? What number times 2 is 5? 2.5. Now it's a balanced chemical equation, except I can't keep the half. So I multiply everything by 2 to get rid of the half. 5, 4, and 2. And now it's a balanced chemical equation. Okay?
And so the coefficients, like the previous problem, we are raising to the power 7 multiplied by. So
That's right.
Product unattracted, so it'd be like negative 349.36 times the
Plus
plus
237.1 times 2.
Got it.
Okay, that's one side. Minus this 209.2 times 2.
Got it.
Okay, what are you guys finding for your delta H of reaction or delta G of reaction here? What? 467 kilojoules per mole. Okay. So is this endothermic or exothermic? Exothermic. This is an exothermic reaction. Okay? Well, I'm sorry. That's not what I'm asking. I'm asking, that's delta H. Is this reaction spontaneous or non-spontaneous? That's what I want to know. This is a spontaneous reaction. Okay? What about this one? That's non-spontaneous. That's a non-spontaneous reaction. Okay? Okay. Let's see here. You guys feel good about that, or do you want to do another example? One more? Okay, let's try this one. C2H6 gas plus O2 gas versus okay, so the only thing we need new here is the C2H6. So let's find C2H6. C2H6 is negative 32.0 kilojoules per mole. Negative 32. Right? 32. Okay, this is at 0. Carbon dioxide and water are still the same as they were above. Okay, what are you guys finding for your coefficients?
2746.
Good. Okay, what do we find for our delta G of reaction here? Okay. Okay. So that should be our delta G of reaction in kilojoules per mole. Okay, that's what you should be getting. Okay, good. All right, let's try a different type of question. Okay, so from delta H and delta S, determine if the following reactions are spontaneous. Okay, so let me remind you that we can try to predict the whether it's spontaneous or not. We're going to calculate it, but we can try to predict it by looking at the signs. Okay? When the signs are the same, that means it's dependent on what? Whether it's spontaneous or not. It's dependent upon the temperature. Okay? If I increase or decrease the temperature, will allow it to become spontaneous or not. Okay? So the signs are the same here. These are both positive, right? Signs are the same as temperature dependent. If the signs are opposite, then the sign of delta G is the same as the sign of delta H. Okay? So I can predict that. So if this was positive, negative, then this would be non-spontaneous at all temperatures because delta G would be the same as the sign of delta H. Okay? All right. So delta G equals delta H minus T delta S. This is the equation we're going to use for this. Okay? So I want to find out whether this is spontaneous or not by using this equation. So pretty straightforward. Delta G equals, actually I'm going to let you guys work on that a little bit, see if you can figure out what. There you go. Okay? Okay, so that's the thing that trips people up the most, is that this is in kilojoules and this is in joules. So you got to convert one or the other to joules or kilojoules. I would say just take this and make it joules. Okay? You find your answer in joules and then convert back to kilojoules in the end. If you don't want to convert back to kilojoules in the end, then convert this one to kilojoules right now and use it. Okay? And oh, good point. It's Kelvin temperatures, right? Kilojoules per mole. It would be spontaneous at all temperatures. Oops, sorry.
Regardless, we always have to convert our Celsius to Kelvin with these problems.
Yes, you do. Okay, somebody find a delta G for this? Say it again. 1.56. Okay. Okay, so we would find 1,560 joules per mole, and we can convert that to 1.56 kilojoules per mole, and that would be our answer. Our delta G for this reaction, 1.56 kilojoule. So is this spontaneous or non-spontaneous? This is non-spontaneous, right? Because my delta G is positive. Good. All right, so let's try another one. Okay, delta H equals 1.8 kilojoules per mole. S. Okay, so we can already predict that this is non-spontaneous, okay, because delta H is positive, delta S is negative, and if the signs are opposite, delta G will be the same as the sign of delta H. So let's go ahead and calculate it here. Okay, delta G equals delta H minus T delta S. Remember, this is at 25 degrees Celsius. Okay, what's the delta G reaction for this? Okay. All right, so 35.5 kilojoules per mole is our delta G. All right, excellent. Now, let's take a break. And we'll do a few more when you get back. Okay. So this is a little bit of a different question. Okay, we're given delta H and delta S, but we're not given the temperature. Right? So we need to find the temperature that makes this reaction spontaneous. We're still going to use the equation delta G equals delta H minus T delta S.
Do you just switch to 0 or one?
It's any temperature.
Yeah, that's a different problem.
Oh, okay.
That's we got for the
Spontaneous.
answer for the last example.
Okay, that's true. So solve. Go ahead. So yes, you set delta G equal to 0. So this is going to help us see that.
Wait, no, because the no, because the delta G is going to be because remember when delta H and delta S are the same sign, the delta G equals delta H. I think that's what he said. And delta H is yeah, I'm trying to the sign is not the same. You can see how it's positive. Delta G equals delta H. I don't know if it's the sign or actually it's just the sign or whatever. It's still confusing. But how are you gonna find it if we're missing two variables? Temperature, true or no? Yeah, how are we gonna tell? Yeah. We know exactly what to do.
I'm sorry? Find it in Kelvin. Good. Okay, let me give you a hint. Okay? So here we're going to assume that the temperature that causes this to go spontaneous or non-spontaneous, okay, is above or below equilibrium temperature. And how do I find that? Well, I find the equilibrium temperature by setting delta G equal to 0. 0 equals delta H minus T delta S. Okay? And then I can simply say that delta H equals T delta S. If I move this term, T delta S, over here, okay? And now, to find the temperature, okay, T equals delta H divided by delta S. This will give me the temperature, okay? That's the equation right there to find the temperature if I set delta G equal to 0. leave it in Kelvin. Okay, so what'd you guys find for your Kelvin temperature here? That doesn't make sense. Why not? It doesn't make sense because this is spontaneous at all temperatures. This proves that. You can't have a negative Kelvin temperature, right? Especially a negative 1500 Kelvin temperature, all right? So this, at any temperature, this reaction is going to be spontaneous, okay? So it doesn't matter what the temperature is, it will be spontaneous. Okay, excellent. So let's try another one.
Dude, what was the last thing you said?
I said that this reaction is going to be spontaneous at all temperatures. Okay?
It's negative? Yeah,
Because delta H is negative, delta S is positive. Okay? You can't come up in that equation, okay, looking at this equation, there is no temperature that you could acquire that would force this term to become positive. Okay? Because if I have a positive temperature, which you always will, okay, because this temperature is impossible, right? So you will always have a positive temperature times your delta S, that term, okay, will always be multiplied by this negative sign here. And so you will always have a negative delta G.
So there is no temperature difference? Then it doesn't.
So it'll be a negative plus a negative, so it always becomes more and more negative. So delta G will always be negative.
And then we can make the assumption that delta G would be negative because delta S and delta H are the same sign.
Are opposite, so delta G is the same as delta H. Okay. Let's try another one here. Delta H equals negative 126 kilojoules per mole. Delta S is equal to 84 joules per Kelvin mole.
Same one?
I'm asking the same question. It's just, oh wait, did I give you the same data?
Yeah, same number.
I'm sorry.
I bet you it's going to be negative 1500.
You would be right. You would be right. Okay, negative 111.7 and negative 105 joules per Kelvin. Yeah, that's better, right?
Ooh, now this one.
This one will have an answer because they're both signs are opposite, right? I mean, same. Signs are the same. So delta G will be affected by the temperature. What is the temperature at equilibrium? Okay, what are you guys finding for the temperature here? Say it louder.
111.4.
Okay, so I have 111 Kelvin, 111.4 Kelvin. All right, and that's going to be the temperature at equilibrium. So we haven't answered the question. At what temperatures will this become spontaneous? So do I have to increase or decrease the temperature here to make it spontaneous? Okay, so if I have 100, let's just say 112, okay? If I have 112 Kelvin, that's going to cause this term to become greater, right? And so it's going to cause it to become more and more positive. That term will become more and more positive, thus overcoming the negative of the delta H and making delta G positive. So at higher temperatures, okay, higher than 111.4, it's becoming what? Non-spontaneous. So we have to obtain temperatures that are what? Lower than 111.4 in order to make this reaction spontaneous. Okay? So at equilibrium, so if I go up in temperature, it becomes non-spontaneous. If I go down in temperature, it becomes spontaneous. Okay? So temperatures lower than 111.4 will give me a spontaneous reaction. Temperatures above 111.4 will give me a non-spontaneous reaction.
So what about if it's at 11?
Then it's at equilibrium. Okay? That's the temperature between that's holding it spontaneous, non-spontaneous equilibrium. Okay? That's why delta G is 0 at that temperature. Okay. All right, I don't think we're going to get it through all these examples today, but we'll finish it up tomorrow. Okay, another type of question. Okay, calculate Kp at 25 degrees Celsius. H2 plus I2 is in equilibrium with 2Hi. Delta G equals 2.60 kilojoules per mole. So we're given our delta G of the reaction. They want me to find Kp. All right, so the equation I want to use is delta G equals negative RT natural log of K, which in this case will be the Kp. All right? We're going to solve for the Kp here. If it was in concentration, we would do the Kc. If it was solubility, we would do the Ksp. Okay? So we're going to solve for our K. Do we know what R is? Yes. Okay? Because why do we want to use 8.314 and not 0.0821? That's right. So does that help you see something about the units here? your constant 8.314 is in joules, and your delta G is in kilojoules. Okay? So. Okay? The constant here is 8.314 joules per Kelvin mole. How do I find? So if I want to get the log of something, I use the log button. If I want to find the anti-log, I use 10 to the x. What am I going to use here that's kind of anti to ln, the natural log? E. I'm going to use e. Good. E to the x. That's right. So now you're going to have to use your e button, which is usually the shift function of the ln, natural log.
I think round it all up.
What are you guys finding?
3.35.
Good. So that's my KP. That's what I'm getting. Okay, good. What is delta G for the autoionization of water at 25 degrees Celsius? What's my K here? Is it a KP? Is it a KC? Is it a KS? Is it a KA? Is it a KB? What is it?
See? No.
In a sense, it is a KC. But for water, it's what?
KW.
There you go. Autoionization of water, KW.
So is that going to be the KW from before?
Yes, that's what you're going to use.
Well, very well.
Excellent. is what?
KW?
KW is is not is unitless.
Units.
It has no units.
So we just keep the R as
Yes, your answer will be in joules.
very well. Very well. See? Sure are.
Okay, what are you guys finding? You have a big number? In joules, you have a big number? Okay.
0.084. KW. No.
0.084.
Units.
No, that's not. 0.084 joules?
It would be joules, yeah.
Okay.
Really?
800? Okay, that's what you should be getting. 79.8 kilojoules per mole for your delta G. So is this spontaneous or non-spontaneous? Non-spontaneous. Okay. That's good. You guys can hate me. Okay, so find delta G at 25 degrees Celsius. KSP is 1.6 times 10 negative 14. It's 2, yes. OH2. Is this what you're talking about?
Yeah, those might be on the other side. Then it's gonna be 2.
Does that matter? For delta G and all that?
For this case, it doesn't really matter, but it could.
Because
We'll see a question where it's going to. So
we already have KSP.
that's right.
So if we didn't have the KSP, then it would matter to figure that out. And then, all right.
Oh, okay. Good. Keep thinking like that, because the next questions will be more like that.
That'll be next. Overachiever.
I didn't see the numbers.
No, I always have a balanced chemical equation. That's a good thing to do. He knows too well that I could give you an unbalanced chemical equation when you need one. So,
It's actually should be almost identical. Last one was 1%. 1.7.
oh, gosh. What were you getting?
78.7 kilojoules.
Yeah.
Yeah.
Okay. Now, I assume this will be the last one we can get to today, but oops. Okay, how am I going to go about this one?
Can we set outright?
G and K. So first, set it to equilibrium, so use a 0.
Yeah, that's what I was thinking.
Find the K. No?
Does it work? Yeah.
Just tell me to fuck off. Part of progression.
How am I going to solve this? How am I going to find the KP?
Set G to 0.
What equation am I going to use to find the KP?
No.
Okay, if I had the concentrations at equilibrium, I could do that, right? Which I don't. So, what equation am I going to use for thermodynamics to find the KP?
Q? The, no.
We've just been using it, right? That's what I'm going to use.
There can be whatever here.
And then you
It's
just
going to find the KP. Yes, to find my KP here. Okay? Now, what information do I not have to be able to find this KP? And that's why they want you to do what? Calculate the delta G. So they're walking you through it. Calculate the delta G, and then use delta G equals negative RTLM to find the KP.
So you have to find the delta G first.
How do I find delta G? We did it. We did the very first thing we did. Yes, products minus reactants. What do I need? I need to go to my chart, okay, and find the delta G of formations for water. The delta G of formation for water in the gas phase.
Wait, so you can always just find the delta G?
228.59. Negative 228.59.
Wait, can we just do that every time when you ask for delta G?
If it's a reaction that, you know, here if I had the delta G table data for all that, then you could, okay? But if they give me all that information, it's easier to just do this. All right?
But hypothetically,
They don't necessarily always have the table data anyways that I need, but in this case they do. 0 and 0.
So that would be possible.
No, times 2.
Multiply it times 2. Yeah. But it's still possible. 'Cause 0 minus
Mhm.
negative. Yeah.
That's right.
Okay.
So yes, the delta G of this reaction would definitely be positive because it's the decomposition of water. H2 plus O2 reacts spontaneously. H2O decomposes non-spontaneously. Now the other reason I know I can use the table data is because the temperatures that they gave me here are at 25 degrees Celsius and the table data is at 25 degrees Celsius. Okay, so what am I finding for my delta G? 457.18 kilojoules per mole. Okay, now you have everything you need, right? Find KP. Hey, make sure you're putting your delta G in joules, right? You guys are converting it to joules. It's in kilojoules here. 457.18 kilojoules. You want to convert that to joules. For the KP? Hold on. Yes. Super duper.
It's like negative 10 to the negative 81.
10 to the negative 82nd? Did you get 81st? Did you switch?
It says 81st here.
How did you get that close?
One decimal off somehow. You just. Okay, so you should be getting 7.2 or around that times 10 to the negative 81. For what? G is the 457.18. But you're going to have to convert that to joules, okay, to be able to use it with your R, which is 8.314 joules per Kelvin.
So the only thing you did wrong. This is 1.2 or 7?
I got 1 point.
7.2?
No, I got 1 point.
It says 7.2.